All right, so this is the end of chapter 3. So we're going to be looking at data, and we're going to revisit the concept of regression. So this is where you enter data into your list 1, list 2, or list 3, list 4, wherever your data's at. And then you can choose from your options in the regression menu, but let's kind of explore that for a minute. So without actually doing anything, let's just look at the menu for regression. If you guys go to Stat and then go over to Calc, there's a lot of things in this menu, but the first one that we used to use for regression way back in the day was linear regression, and that was pretty obvious to tell because it looked like a line. And then there's quadratic regression, so your scatter plot would look like a quadratic function, a parabola of some sort. We have done that before. There's cubic regression. That one's a little harder for kids to identify, but it looks like a cubic function. Quartic would look like a W, like a quartic function. There's another version of linear regression that inverts the x and y variable, so sometimes that's what you need, and whatever. We never really used that one unless it was by accident, I suppose. This one, what do you think that stands for? Natural logarithm. Very good. So if ever I ask you to perform a logarithmic regression, you have to choose natural log regression. That's the one that they utilize in the regression function. Simply because many of these questions are like based in nature, and a natural logarithm is a fine fit for all of those, if that's the pattern that you see. So there's exponential regression, which would be like your exponential functions that we have been working with, where it like starts off low and then grows really rapidly, very fast. Power regression, we saw that a while back. We're not going to see that too much today. And then there's this guy, logistic. Now, when kids hear logistic, their brain thinks logarithm. Those are two different words, yeah? They have nothing to do with each other, okay? So logistic growth, I should call it. Logistic growth is like the bear problem from yesterday. Do you remember the bears from yesterday? They were left in their habitat, and then they reproduced for rapidly, at a rapid rate, and then it kind of flattened out. Because like nature takes its course. There's only so many like raw materials out there. They kill each other eventually. So it's what's called a carrying capacity in nature. So there's a big flag today that if you're dealing with a natural problem where it's like population of an animal, or sometimes it's about like mold in a petri dish, like there's a certain carrying capacity to that where there's not enough supply to sustain the life, so it doesn't continue to grow and it will flatten out. So a lot of kids are like, well, wait, that's kind of what a logarithm does. Like a logarithm flattens out. The difference is a logarithm doesn't flatten out. It grows slowly towards the end of its domain. And here's the key difference today. A logarithm regression, frankly, I'll probably just tell you, use logarithm regression. The only time you would choose logistic growth is if A, I told you to do it, or B, if it's one of those nature problems where there's a population of bears, a population of deer, a population of bacteria, like I said, in a petri dish. So that's how you're going to know which one to choose. The part of the lesson today that we're going to be skipping is when we get to what's called linearizing the data. Skip that part. And that's because it's just too much fun to have. We don't need to have it. Okay. I'll show you what I mean in a minute. So remember, exponential growth looks like so. Logarithmic growth looks like so. Notice it doesn't flatten out to a complete horizontal asymptote like logistic will. And let's look at this guy. So everybody on their calculator, please. My data is going to be in various places. So I am going to enter, it already is entered thanks to first hour. I'm going to enter my data into list 1 and list 2. I want you guys to do the same. As soon as I can get my pen to work, I'll write that down. Oh my goodness. There we go. So this is going to be list 1 and list 2 for me. However, remember, we don't put calendar years in our list because it makes your data really screwy. It does say X represents the number of years since 1950. So 1950 is going to be year 0. 1960 is year 10, 1970 is year 20, and so on and so on. So I'm going to pause the video, and I'm just going to take a break while you guys get all this data entered. Pause the video yourself, viewers. So my data is entered into list 1 and list 2, and the next thing I want you to do is check out the scatter plot. So in y equals, I have some old equation from a previous question, so I need to delete that out. Make sure your y equals is currently empty. And then the other thing I need to do, because I've been playing around with scatter plots a lot today, I need to turn on plot 1, because that's where I'm graphing list 1 versus list 2, and make sure it's a scatter plot that you're graphing. The other thing I need to do is I need to turn off my plot 3. We were working hard in first hour, so. All right. So plot 1 is turned on. The window's probably messed up because I haven't done anything to adjust the window from my last question. So the easiest way to get a nice fitting window for your scatter plot is to do zoom stat, which is zoom 9. And you should see this shape. So in a lot of the homework questions, it says like draw your scatter plot. So you guys would just kind of transfer this to your paper. It doesn't have to be super accurate, but relatively accurate. And then discuss with me, what kind of shape do you think you see? Exponential? Yeah. Did you go with exponential? Okay. Yeah. And some kids were like, well, it kind of looks like part of a parabola, quadratic. Yeah, I gotcha. Like, you could make an argument that you think it's quadratic, but it turns out exponential is the better fit in this case. So we're going to go to stat, and then over to calculate, and you're going to go down until you see exponential regression, which I believe is 0. Yep. All right, so it's going to prompt me and ask me where my data is. I remember my data is in list 1 and list 2. And then I need everybody remembering how they store the regression equation into Y1. Do you remember how we do this? What's the quick way? We do alpha trace. That would take us to the quick key for F4. And then Y1 is the first one that pops up. On the older calculators, you have to go and get it the old way. So you have to go to varies, Y varies, function, Y1, all that stuff. All right, so it's storing the equation at the same time that it's calculating everything for me. So now I would take this info and I would write it down on my paper. Now, notice exponential equation in the form a times b to the x power. So a being our initial value and b being the base of the exponential. These is the r's are the correlation coefficients for r equals 0.999. Tells me that's a pretty stinking good fit. If this r didn't show up, that's because you don't have your diagnostics on. So if you go to mode and you have stat diagnostics down here, you can manually turn them on just with that quick key there. But anyways, I need to go back to my paper now. And I need to move forward. Here we go. I need to write down my equation. So remember, the general form from our calculator was a times b to the x power, and it kind of writes it weird because of the script that your calculator uses. Where we go? Who's not A? So the a value, I'm going to have to round, obviously, 1812.01. And then I like to put the base in parentheses. I just think it helps my brain kind of realize what's going on. Because if you think about what the exponential function really says, it's like the initial value times 1 plus the rate to the x power. That's the formula. Remember, this guy was really like 1 plus r in the formula, which helps me with my previous question, which I skipped over like a silly person. It says, what is the growth rate? Well, right here, this 1.035, that was the part that was in the parentheses, right? And if you think of this as 1 plus r, that means the r was the 0.035 part of that, better known as 3.5%. So you can still pull out like the pertinent information from this regression model. It's the same as the original formula, the a times b to the x. There's no transformations in it, obviously. They try to center it at 0. Or center it with no transformations. All right. There's one more follow-up question, though. It says, estimate the GDP in 2020. So remember, your years we're measuring since the year 1950. So what does that mean? 70 years later? So what I would like you to do is to use your calculator equation, not your truncated one. And I want you to plug in x equals 70. All right, so here's where you have some options. You can either go to table set and change your table so that the independent variable is in ask mode. And then when you go to your table, you can just type in whatever x you want to type in, right? So there you go. Now, there is a bit of a warning here, guys. You have to highlight the actual number in the y column to get like the full value, and that way it won't like truncate and round it off. The other way to get that answer is if you guys look at the graph. Now it's going to graph my function with the scatter plot. I can just do the trace typing thing to find values. However, right now my window is stopping at x equals 55 for a maximum. I'm going to need to go past 70 in order to find it. So I'm going to go to 75. And then when I hit trace, it starts on the scatter plot. See, it says plot. So if I hit the up arrow, it'll hop onto the actual function, this disgusting function that it didn't round off. And then when I type 70, that's another way for me to plug in a 70. So you just have to kind of choose which way you would like to make the calculator plug in 70, so that way you don't use the truncated function.
Wait.
Mm-hmm.
How do you make it so you can type 70?
You hit trace first.
Yep.
And then you're going to be on the scatter plot at first, which doesn't work. So you use the up arrow to hop onto the other function. Because remember, it's graphing two things at one time. The scatter plot and the function.
Okay.
And then you can type 70 and hit enter.
Got it.
So I don't really like messing with my table mode. It bothers me because I usually don't want it in ask mode. I guess potato at this point, right? Like potato tomato. All right. What value did you get, by the way?
I don't know.
I didn't write it down. 19 something.
1995850.84.
Okay, and that would be like a surely super exact answer from our model. Just fun fact: if you guys were to plug in 70 into this truncated model, you get a very different answer. Okay, so that's why we're really encouraging you guys, unless it states otherwise, to always use your calculator's non-truncated equation. All right, here, this is the bear problem from yesterday. So when you have typically a nature problem that involves population of an animal or something that's alive and feeds off of nature, you get what's called a logistic growth function. So that is one of the options in our regression menu, so that's fun. And then this is the logistic growth equation, which by no means am I going to make you memorize. Fun times. But what you're going to notice about logistic growth is it grows rapidly until it hits what's called a carrying capacity. So a carrying capacity would be basically like there's not enough natural resources, space, whatever, for it to continue to grow without bound, and it just kind of maxes out of the population. Obviously, there's things that can happen in nature that changes that carrying capacity, but for a certain amount of the domain, they reach a carrying capacity. Fun fact, you might want to note this on your notes. This C up here, that is the carrying capacity number. So if it starts off with like a 300 divided by stuff, 300 is going to be the carrying capacity of that function. All right, so let's get some data entered here. There's a very little bit of info at the top. It's the number of mice living in a certain habitat. So right away, your brain should be thinking, oh, I bet this is a logistic function. However, if you keep reading, it says find the logistic function. So I'm going to pause the video. Viewers are pausing their video, getting your data entered into wherever you want. My data is going into list 3 and list 4 because it's already there. So on my calculator, not here. Go clear that baby out. I have my data entered into list 3 and list 4. So when I go to mess with my scatter plot, I'm going to turn on plot 2. Which means I got to turn off plot 1. So just make sure that wherever you think your data is, that's the plot that you're turning on. And you have it set up to graph the right data. And then we are going to go to stat over to calc. Now this is where sometimes kids get confused because I understand logarithm and logistic like kind of get the same in your brain. I want the logistic growth regression. So you got to scroll down or up. I think it's B. Yep. Choose logistic. And then make sure your data is coming from the right place. So mine's in list 3 and list 4. I don't know where yours is. I would like you guys all to get in the habit of always storing your equation. So I'm going to use that quick key, alpha trace. And then let's calculate. Now, this is a lot to look at when it actually calculates it. It takes that really disgusting formula and it writes it horizontally, so you're going to see a ridiculous number of parentheses. So what you might want to do on your notes is just jot this part of it down and write it vertically instead of horizontally. So then when they give you the coefficients for A and B and C, you can just kindly plug them into the formula that you're used to seeing, or you will be used to seeing after you do a few examples with me. All right, where are we at, mice? So the function, the logistic growth function is y equals, can we just agree that that C value rounds to 10? So 10 over 1 plus I'm just going to round, if you don't mind, 2.36. I do mind. I need exact numbers. These are mice. All right, negative. Is it, like, I don't know. I don't know what it rounds to. I kind of wrote that down. I hope that's right. Okay, cool. So the point is, I don't really care because I'm not going to use that rounded function anymore. I'm going to use my calculator because remember we stored it. So I need you to somehow plug in x equals 20, whether it's on your ask mode of your table or whether you adjust your graph so you can plug it in that way. Where are you at, calculator? I'm going to go to my table. I already had it set up in ask mode, so might as well. 20. Oh, look at that. There's approximately 10 mice. And now I remember something that my very wise teacher just told me. Do you remember what I said this top number was? It's a 10, yes. Do you remember what I said it was about the function and about the... Yeah, it's called the carrying capacity, but limit's another good word for it. So make a conjecture about why the logistic model may fit the data. It's the population of mice. Seems, whoops, that's an E, to reach a carrying capacity. Well, this is one of those you'd restrict the domain based on, like, no, I can't have negative mice. You know? So, well, I can't have negative time. It's confusing. So, like, when you make a regression model, it's based on a certain amount of data restrictions. So, like, for the years, like in the GDP question, like for the years between 1950 and 2000, like this is the model that fits the data. If you go to the years before 1950, it's very possible that that model doesn't fit the data anymore and you can't use it. So, like this question is about mice, and yeah, there's not enough information in this question for me to kind of deduce whether we could extrapolate out of this one. We're trying to extrapolate into the future. All right, carrying capacity of 10 mice. I'm assuming it means like per like cell or something. I don't know. There's no information on this question, so I don't really know what the 10 even means at this point. I don't know what the X means, I should say. All right. Take a look at, so this is out of your textbook. It's some examples of different regressions. And I don't know if you've caught on to this or not, guys, but some of our regressions don't give you correlation coefficients. Like, they don't tell you R's. So you wouldn't be able to determine whether it's a good fit or not. So, like, this guy, linear, quadratic, power, exponential, and logarithmic, they were able to calculate R's and whether they fit or not. I don't know why that was not fitting very well at all. And then the logistic regression is not really any... It's a really bad picture of it, by the way, but that's not anything that it's showing. But notice this data. How do you know which one fits the best? It's all the same data set. Have you caught on to that?
What?
The plots are all the same?
Yeah.
Yeah. Now, they tried fitting them to linear, quadratic, power, exponential. So I heard a lot of people voting for exponential. Yeah, and why would you kind of step away from logistic for this particular question? What do you notice it's not doing? Yeah, I don't know if it does this off to the side. I have to kind of extend the window, and clearly if this is the end of the data, it's not going to have a chance to do that. So I don't think logistic is a wise choice. Because a lot of people look at this and they go, oh, but it fits so nice. Not really, because one of the things logistic has to have happen is it reaches that carrying capacity. So if you don't see that, then no.
It's just as nice as the exponential.
But the whole point of logistic,
right.
Yeah. And that's why it gets tricky, right? So here's what's going on. Can we all agree this is not a line? Can you all agree a quadratic doesn't fit this real nice? Power regression like kind of fits, and then it gets a little weird at the end. And that's why you see a correlation coefficient of 0.94, but that's nothing when you compare it to the 0.99 that exponential gave you. So here's the problem. Not all of them actually give you correlation coefficients. So like there is a school of thought out there that's like, well, I don't know, I'm just going to make a guess and check the correlation coefficient, and if it's good enough, I'm going to use it. And that is how it is approached in some stats classes. But technically speaking, we can do what's called linearizing the data. Now this, notice, has a big red line through it. We're not going to do this. But let me show you what we could be doing, okay? In your calculator, if we made you do this, here's what you would do. You would put your data into list 1 and list 2. So list 1 would be like all your x's, and list 2 would be all your y's, just like you always would enter it. But then in list 3 and list 4, in list 3 you'd plot the natural log of x, so natural log of list 1. And then in list 4 you'd plot, or you'd calculate, the natural log of list 2, so natural log of list y. The other thing they'd make you do is in list 5, you'd have to compute the square root of list 2, so that would be like the square root of y. It's not like crazy, because your calculator has a very small amount of like programming capabilities in this menu. So what you would do is you'd go up to like the name of list 3, and in the name part, you would type a command. You type natural log list 1, and then when you hit enter, it would autofill the whole column of the list with all of the data that you want. So it's not like crazy. So here's what would happen then. If you plotted the natural log of x versus the natural log of y, and you saw essentially a line, you saw a really good line, you have a power function relationship. If you plotted x comma square root of y, and you created a line, that means your data has a quadratic relationship. If you plotted x comma natural log of y, and you saw a line, that means your data had an exponential relationship. And then if you plotted natural log of y versus natural log of x versus y, that means your data, and it showed a line, that means your data has a logarithmic relationship. So what you're doing in that stuff that's all highlighted there is you're taking what are nonlinear relationships and you're linearizing them. Gosh, I can't say that word. Think about this, guys. A power function, I'll ignore the power. Let's look at an easier one. A quadratic function. To undo the quadratic component of it, wouldn't you just square root the terms? So they're taking what used to be a parabola-looking shape relationship, and when they square root the y's, they create a line. Your eyes are glazed over. That's good news, because we're not going to do this. All right, so here's what's going to happen on your homework. You're going to look at your scatter plots, and you're going to go, methinks that looks like a logarithm, and then you're going to use logarithm, okay? And you're going to look at your data and go, methinks that looks like an exponential function, and you're going to use an exponential function. And then on the test, I'm going to do even better. I'm just going to say, use a logarithm, okay? So you don't have to do all this business. This is a good time for a different class, I think. A different class. Maybe a stats class. I don't think they do this in stats. All right, so we're not going to do any of this business. So when we get to our homework, I'm going to have you scribble out some of the directions on some of the questions. All right, let's try this guy. Can you please get this data entered? My information, now this is about a computer virus spreading to various machines. So get your data entered wherever you want. Mine is going into list 5 and list 6. Pause, get your data entered. All right, so my data, I believe, is in 5 and 6. Let's double check that though. Yep, there's all your computers and viruses. All right, so y equals, clear out the last one we did, turn on your plot to graph the appropriate data. I'm going to turn on list 3, or plot 3. Mm-hmm.
You wouldn't use Logistic for that, right?
No.
Because it doesn't run out of resources.
Right.
But if that was, say, a virus for humans, would you use Logistic?
Well, pertaining to the growth of the virus, I would say no, and here's why. Because with few exceptions in history, well, actually no exceptions in history.
Viruses don't require very much to stay alive.
Well, eventually something happens in nature where they no longer are prevalent. They slow, and this happens with computer viruses too. Humans, like, combat it in some way. So they either, like, limit the exposure, like back in medieval ages, they would just say, oh, you're sick, get away, and then they would push everyone away, and like if you showed any symptoms, they just let you go off and die. You know, nowadays we go, oh, we're going to quarantine people, and we're going to try to medicate them as best we can with our technology available. And it's like for computer viruses, what you're noticing is while it doesn't reach a carrying capacity, it does slow, because people are now aware of the computer virus, so they know not to open an email that says this, or they know not to do things that are risky, like give kids Wi-Fi passwords. Oops, sorry, hot button. So that's why, that's a great question, Daniel. So it's not a logistic growth problem, because it's not that it's reaching a carrying capacity, it's that it's countermeasures are being put in place that slows the growth of it. I'm not saying, like, when computer viruses start spreading, that all of a sudden they just reach a maximum and then they stop. It slows, but there's still, like, that one person 2 years from now who's going to get that computer virus, right? Some poor person out there who forgot that they shouldn't open that attachment, you know. It's usually... It's grandma. Oh, poor grandma. All right. So let's go ahead and look at our scatter plot. Let's zoom 9 that. So this is where some kids start getting confused, and I'm glad Danielle brought that up, because they're like, oh, it's flattening out. Okay, remember, this is not a natural nature, like, there's only so many resources problem. It is slowing down, which indicates this is a logarithmic growth, not to be confused with logistic growth. So this is where kids get into trouble. They go to stat, they go to calc, and they're like, logarithm, 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 and what do you think they choose? They're supposed to choose 9, but what do some kids choose? Some kids go logistic because their brain goes log, 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 everything with log. All right, logistic, not a logarithm. Don't choose that one. Please choose number 9, the natural logarithm regression. List 5 and list 6 is where my data is. Please store your function into Y1. I'm so happy she taught me that quick way. I totally forgot about these quick keys. There's a lot of cool things hidden in those quick keys. Go explore them one day. It's not working for you.
No.
Like the data doesn't look right?
Like it's not plotting.
Did you zoom 9 it?
Yeah.
Okay. Go to y equals. And which plot did you have turned on?
1 second. I had plot 1 turned on and plot 2 and 3 are off.
Okay. Is your data in list 3 and list 1 and list 2?
Yeah.
Okay. Just go to second y equals and open up plot 1. Yours should be turned on. It should say scatter plot and should say list 1, list 2.
Turned off?
How dare you turn your plot off? Okay, we'll turn it back on.
Because I just reset all the...
Oh, yeah. That'll do it. All right. So, oops, I need to back out of here. Beep. There we go. There's my logarithm equation. Now, if the order of the terms bothers you and you're like, why are they putting A+ at the beginning? Then rewrite it. I don't care. But the important part is it's, let's see, 614.37 plus 217.41 times the natural log of x. And that is a stinking good fit. Look at that.
Yeah, it's 100%.
Yeah. All right, so we're going to... No, we're not, Abruzzo. Come on. Turn page. Remember, we're not doing that testing thing. So on page 14a, you guys should be able to write down your equation now, which I already forgot. So it's 614 points. I'm just going to round to 4. Plus 217.4 times the natural log of x. There is your equation. Why is that line so little? So now notice what the book had them do. They really truncated this formula. So they really rounded off to the nearest whole number, which I think was a little bit dangerous. However, we already could accept the fact that this was a regression equation to begin with, so it's not like 100% accurate anyways. And we're just talking about like the spread of a computer virus. So is it very important that you're truncating? Maybe not. But notice when they do this in your, can you guys do this for me in a second? Can you type this in your home screen? And I think you get like 1091-ish. Oh, 1092. Okay. Was that from the home screen, not from the calculator? Did you just type this exact thing in your home screen? Okay, that's what I need you to do. It is awkward. I'm recording all of it. Now the world knows.
Wait, why is it 109? It should be 1092.
1090 point what?
1092.
So rounds to 1091?
How?
No. So yes, 1091 if you're out of this whole computer. Yeah. Okay. Now, the reason I wanted to do that, look, what's the difference if we use the calculator equation? So, not a significant difference, right? So that's why they didn't...
Not even a whole one, almost a one.
I thought it came out to like 192 something.
It's 1091.97.
1091.
91.975.
Okay, so 1092. Very little difference because of the truncated equation, okay? Because, think about what happens at the end of a logarithm. It's very slow to grow, right? So, in an exponential, you have extreme differences if you round off and truncate. In a logarithm, you really don't. So that's why your book had no qualms about saying like, ugh, whatever, just round it. So, on a test, we don't really ever want to round things off because I'm always going to ask you, most of the time I'm going to ask you to always use the stored regression equation from your calculator. And in many cases, it will make a difference. Logarithms, it really won't. But there will be a time in the future where I say, like, please round to the nearest 10th. And then everyone has to kind of follow suit because we're going to try to express to you what happens when you round an equation versus what the true value is. There's a question coming up in your future where we have to really follow directions on rounding. Sometimes you guys, no offense, not super good about rounding to the appropriate spot when I ask you to. Okay? So pay more close attention to that. That's going to be important in our future. All right, could you all find worksheet, well, not find, just flip over to worksheet 14B. This is where your assignment starts for tonight. Where'd you go? There you are. And number 1, go ahead and start typing that data into list 1 and list 2, please.
Oh, I didn't think you were here.
All right, so my class is entering this data. This is for their homework. So list 1 and list 2. And I'm about to graph a horrible rendition of what the scatter plot looks like. Something like this. So one of the changes that we're making to your homework assignment, because we eliminated it from your lesson, where it says, which model do you suggest? That's fine, but I don't need you guys doing all this business with the testing, and is it linear, and no, we're not doing that. So use just your knowledge of functions. Which one do you think would be an appropriate fit for this particular shape? Exponential would be a great fit. And if this was a test, I would just flat out tell you to use exponential. You wouldn't even have to guess about that, okay? So you guys are going to figure out your exponential model using regression. You're going to write down your equation, and then you're going to probably just use your calculator to plug in x equals 20. I'm going to pause the video just so you guys can finish that question since you're in the middle of it, and it is a homework assignment.
It's already ruined.
All right, so when you guys move on, this scatter plot, guys, this is going to look like this. So since there's no reference here about whether it's nature or not, you can't use Logistic because you don't know if it like has a carrying capacity. But maybe a logarithm would be good. Okay. You'll notice when to use Logistic because it'll talk about population of animals or people or something. So like here, this is the population of a rat. So that's why it's encouraging you guys to use the Logistic model. And then continuing on, we got population. This is on the next worksheet, I think. Now, I know I just said if it's population, it's always Logistic, but that's not really true for people. Because apparently we're the dominant species, so we just keep overtaking things. So this one ends up looking like this. So you're going to see an exponential. So remember, guys, you're not doing any of the testing. None of this testing. Get out of here, testing. And then this next one here talks about a petri dish, which is a limited environment, so they're going to ask you to do logistic. They'll flat out tell you that. And then there's a bunch of questions coming up here where we crossed them off. So like we're not doing 6, we're not doing 7. Oops, we're not doing 8 either. But you totally need to do number 9. And then again, this time it's about fish in a lake. So that is a limiting environment, and we're going to have a carrying capacity. So logistic model is the way to go in that one. All right, good luck.